Our team has built a hardware project which measures value of capacitor without using Arduino or any kind of microcontroller. So the objective of our project is to measure unknown capacitance value and display value on 7 segment display. So let me show you the concept we have used in this project to measure the capacitance. Here we have used concept of time constant of capacitor. Let me show you by giving an example. So here is a circuit which has a 5-volt source, a switch, a resistance R, and an unknown capacitance C. And let's take the value of the voltage source 5 volt. So we will calculate the value of unknown capacitance by the formula C equals to T by R, where C is the unknown capacitance, R is the resistance value given in the circuit, and T is the time required for capacitor to reach 63% of the maximum supply voltage, which here is 5 volt. Let me show you it on the graph. Here the graph is charging of capacitance with voltage against time. So when the value of the capacitor charge reaches up to 3.15 volt, which is 63% of 5 volt, at that time the value of the time is the T we will use in this formula. So let me take the value of R equals to 1.8 kilo ohm. Here we are assuming the value of R, and the time T it will take to charge the capacitance C up to 3.15 volt is 3.92 millisecond. So the capacitance we get here is 2.17 microfarad. So this is the concept we are going to use to measure the capacitance in our project. So what's the significance of this project? Why are we building it? So the reason behind to build this project is that in EC laboratories or any other IoT laboratories, we often come across different sizes of capacitors which don't have value printed on them, or the printed value is somehow erased. In that case, it's difficult to identify the value of capacitance. Many multimeters have inbuilt circuit to measure capacitance, but they are a bit expensive. So we came up with a cheap version of the capacitance meter. Now let me explain you about how the circuit works. So there are 3 main units in this circuit. First one is the oscillator circuit. Second one is the comparator circuit, which compares the voltage, and third one is the counter circuit and the display circuit. So first of all, here in oscillator circuit we have used CD4060 IC to generate 250 kilohertz of frequency through oscillator. We have used crystal oscillator to interface with the CD4060 IC. We have used pin number 7 of the IC Q3 as an output pin of the IC. So here the question arises, why we have used 4 megahertz crystal? Why didn't we use any other crystal? So to answer that, we need to understand what happens at Q3. So let me explain what happens at Q3. So at Q3, we need 16 pulses to form one cycle. So to get 250 kilohertz frequency at output according to that we have choose crystal of 4 megahertz. So when we multiply 250 kilohertz frequency with 16 pulses, we get 4 megahertz crystal. That's the reason we have take 4 megahertz crystal in our project. So the output of this IC has given to the first IC of the counter circuit as a clock. Now let's move to the second part, which is comparator circuit. We have used LM358 op-amp to compare two voltages. One voltage is 63% of 5 volt, which is 3.15 volt, and other one is the capacitor voltage, and the output of op-amp is connected to D flip-flop IC 4013. So when the voltages are equal, 3.15 volt equals to capacitor voltage, or we can say capacitor is charged up to 3.15 volt, output of op-amp is set to 1 and it is given to the reset input of D flip-flop, which turns on the LED, which indicates that the testing is done. At last we have counter circuit, but before that we need to understand these three switches. So switch B and C resets the whole circuit, including all counter ICs, and discharges the capacitor, which we are going to plug here to measure the value of the capacitance, and switch A charges the capacitor. For counting circuit, we have used 4026 Johnson upbeat counter IC, and we have used 6 such ICs. The 250 kilohertz frequency we have produced here goes to first IC as a clock here. And the carry of the first IC goes to clock of second IC, and so on. As soon as the 3.15 volt mark is reached, the oscillator stops the pulse train, and the pulses which have passed are further displayed in the form of value of capacitor. From the left, the first 3 digits are on the left side of the decimal point, and the other 3 are on the right side of the decimal point. The measuring unit of this system is in microfarad. So let me give you a demo of this circuit, that how it's gonna work. So here we have 3 capacitors, 1 microfarad, 10 microfarad and 100 microfarad, which have values printed on them, but we are gonna cross check how much accurate is this project. So let's try with the 1 microfarad. So I'm gonna plug it in here. So we have to mind the positive and negative leg of the capacitor. So we plug the capacitor of 1 microfarad. Now we are gonna reset the circuit. Here we have reset the circuit. Now we have to just test the capacitor by pushing the push button A, and we have to push until the LED glows on. Here we have value 0.948, which is 0.948 microfarad. That's plus or minus 5% error. We are going to reset the circuit. So for 1 microfarad, the circuit shows 0.947 microfarad. We are going to test 10 microfarad capacitor. Okay. Again we have to mind the negative and positive leg of the capacitor. I plug the capacitor. Now we're going to reset the circuit. Now we are going to test it. Here we have 12.532 microfarad, which is close to, a little bit far, but still close to 10 microfarad. At last we are going to test 100 microfarad capacitor. Reset the circuit. Reset. Test. So here we have seen that it takes a bit time to process the value of the capacitance, as the capacitance value is high, 100 microfarad. So the value we get is 125.108 microfarad, which is a bit far but still close to 100 microfarad. Thank you.